If you're going to be running a very elite research institution, you have to have the best people. And to have the best people, you have to trust the people and empower them. You can't hire a world expert in some area and then tell them what to do. They know more than you do. They're smarter than you are in their area, right? Yeah. So you've got to trust your people. And so one of our really foundational commitments, as I said before, to our people is we trust you. We're going to work to empower you. Go do the thing that you need to do. And so if somebody in the labs, wants to spend 5, 10, 15 years working on something they think is really important, they're empowered to do that.
Welcome to Analyse Asia, the premier podcast dedicated to dissecting the pulse of business, technology, and media in Asia. I'm Bernard Leong. As AI reshapes our digital future, infrastructure becomes the critical differentiator. With me today is Doug Berger, Technical Fellow and Corporate Vice President, Microsoft Research, to dive into how the innovations in AI infrastructure, from custom hardware to regionally grounded research, are now redefining what's possible. Doug, welcome to the show, and first, congratulations on the launch of Microsoft Research Asia in Singapore. And welcome to Singapore.
Yes, thank you very much. I'm really, really happy to be here. Opening the lab here in Singapore is exciting to me because it's my first trip to the region, and now I'll have an excuse to come back many times.
Great. And before we start, I've also done some research on your background, but I want to, which actually is between in the midst of academia and bringing them to real life applications. So maybe we start with your personal journey. How do you get started in computer architecture and then subsequently AI research?
Like many people, I think which field I chose was an accident. I went to graduate school for my PhD in computer science, and I took a course from Guri Sohi, who was a professor there who was teaching computer architecture, and I just loved it. And so that was it. It was one of these happenstance things. I went and got my PhD in that area and then moved to form a research group at the University of Texas at Austin.
Then eventually, how did you ended up with Microsoft then?
I spent, with my colleague Steve Keckler, we spent about 7 years building for academia, a crazy new processing chip. And it was funded by the US government. It was a ton of work. A really fun project. But after that, you're coming off the sugar rush of the big project and wondering what's next. And Microsoft came calling about the time I was wondering what I was going to do next. So it was just good timing. And they recruited me up to the corporate headquarters in Redmond.
So I think one interesting question I probably have, you went from academic, like a professor, to now a corporate vice president at Microsoft, right? What are the key decisions that shape your trajectory moving from academia to real-world applications type research?
I think the biggest thing for me was just always wanting to feel challenged. Like whenever a job has felt a little bit too easy, I get restless. And this is career advice I give to junior people. If you're not growing, if you're starting to feel like you're turning the crank, move and do something hard. I think that's probably the biggest factor.
And I think that's a great life advice. So I want to first quickly dive into one of the subjects of the day, but it's actually regarding Microsoft Research. Now in Singapore, it's also going to be a regional research and development frontier. So it is the first lab in Southeast Asia. What motivated this expansion now, and why Singapore?
If you look at, so MSR has been around for over 3 decades. We're, by industrial standards, a very old lab, but we've actually grown quite a bit in the number of regional labs we have over the last 5 years. And part of the reason is that with this AI transition, it's really important that we tap into local pools of talent, local culture, different ways of operating, because we really want AI to work for everyone. And so I think some of the unique characteristics of Singapore, certainly the great local universities, the talent, make it a very good place to put a lab, really innovate in AI in a way that is appropriate to Singapore. And so we will learn from all of this. We have labs in Africa, we have labs in Europe, we have labs in North America, of course, and other places in Asia. But that geodiversity is allowing us, I think, to build better AI that works for everyone, not just the companies that trained it in one location.
So what would be the lab's strategic direction, and how would it tie into, say, Microsoft's broader research objectives?
Initially, the lab is going to be looking at, of course, foundational AI, embodied or physical AI, health and AI and health. And so there'll be a few initial focus areas, in part because of the local interests and the local collaborations, and in part just because of the talent that we hire. And that's the expertise that we have right now. as we grow, of course, we'll move into different areas. One of the things that I'm really excited though is when we start a new lab, and then those researchers who, as we hire more talent, they get plugged into the global Microsoft research network.
Yes.
And they just start learning from all of these incredible people we have across many areas around the globe.
I'm actually a very beneficiary of the Microsoft Research Center in Cambridge when I was working first in cosmology and then went into the Human Genome Project. And Chris Bishop from Microsoft Research Cambridge was one of the academics that I learned a lot, that I actually looked at a lot of his work on Bayesian networks that actually helped me with unsupervised learning. So I know that there is actually even an ecosystem that's being built up from the lab to its external environment around them.
Right, and when we have interns come here, or PhD fellows and collaborations with the local universities, but then full-time employees, they're part of that global network, and they can tap into people like Chris. And Chris, by the way, is just such an amazing person.
Yeah.
I count myself very lucky to be working with him in MSR.
I'm probably going to catch you when I visit Cambridge in this coming winter. So I will catch up on that later. But one of the interesting things that really excites me is the lab's healthcare initiatives that stood up to me. I think using AI to detect seizures or epilepsy in children, and also applying computer vision to assess motor function in Parkinson's patients. How is Microsoft Research advancing these technologies, and what does this signal about the potential for AI to support early diagnosis or personalized treatment in healthcare?
Well, I think you know as well as I do that AI is really good at finding patterns in large amounts of data that we don't see.
Yes.
And so, the MSRA teams have already found some of those patterns that will help people. And you mentioned some of them, Parkinson's, Alzheimer's, cleft palate. We have in Africa, we have an initiative looking for premature retinopathy in babies and preventing blindness. And so I think there's just so much opportunity as our AI technologies advance to find more and more of these patterns and help people with preventative diagnostics. And I think the partnerships here in Singapore in particular with Sing Health and the government and the pools of data will provide a way to do that and really help people. And then when we do that here, another really important factor is when we come up with something here, we can span it across the globe. So discoveries that help the people in Singapore through these collaborations eventually go global.
Yeah, I think specifically for the cleft palate case, because my eldest daughter is actually a cleft patient. I think she was blessed because Singapore has one of the best cleft centers. I think even there was a Berkeley genomics specialist who I know, who was very well known, was actually getting genomics data here through them. And I think there is the Operation Smart where they need to go to all the surrounding countries. It's actually 1 in 70 Asians actually has a chance of getting cleft palate, which is not very unfortunate.
Right.
There. And I think being able to help those kind of detection, what you're doing in the Microsoft research will be pretty good, not just for here, but also for the rest of the world.
Yeah, that's when these stories become personal, they become very moving. So I'm actually really happy to hear that this is important to you.
I think there is also now a strong emphasis on thinking about regionally relevant, because given Southeast Asia have a diverse set of language, diverse set of cultures, and because we're talking about foundational AI, from what your teams are going to be interesting, and also responsible AI. How are you embedding Southeast Asia's societal norms and values into the research center?
So if you look globally at MSR, we actually are doing this in many places now. So we have initiatives in Africa, we have initiatives in India that are looking at building models that work well with uncommon languages to make them accessible to everybody. We have work looking at adhering to cultural norms, and when images are generated, making sure that they're representative of the local cultures and not just the data sets that they were trained on. And so, as I was saying before, those technologies that we're developing will be able to be applied here. But now we can also use them with the local culture, the local languages. And I think this is part of our goal to really make AI accessible to everybody in a way that's equitable and sort of not coming in from the outside with something that doesn't work for the culture.
And it also aligns with like the Microsoft's responsible AI. I know
Yes.
Brett wrote a book on this subject, talking about how to embed responsible AI into the realm of all the technologies that you are building out.
That's right. And when I read through, the summary of your, Singapore National AI Strategy 2.0,
Yes.
there was a big focus on responsible AI and privacy and safety and accountability, and those for us are also very important elements. And so in MSR across the globe, we actually have many teams working on all of those problems to really make this safe for everybody.
That's very interesting. One key thing before we get into much more interesting subject would be Microsoft is actually partnering with institutions like SingHealth, the National University of Singapore, Nanyang Technological University, and Singapore Management University. Can you just elaborate on some of these collaborations and their early impact?
Well, what I would say, maybe I'll start at the very high level. So I think many of your listeners may not know that much about MSR before this, but
yes, correct.
We are fundamentally an open research organization. About 80% of the papers that we publish are actually done jointly with academics around the world.
Yes.
And so we are very open, we are very collaborative. You know, we publish most of the work that we do, we open source much of the work that we produce. And our researchers are also given huge amounts of autonomy to go and do the fundamental research that they think is most important. So one of the great and hard things about my job is I can't tell anyone what to do. Right. And for Peter, you know, my boss, it's the same thing. So, you know, we really, I mean, I can have an opinion and I can share it, but I can't tell a researcher, you have to go do this. That's part of our contract. And so everyone is really asked to do the most important things that they can do, whether it's some fundamental research or some curiosity-driven thing, or taking a technology that we've developed or a breakthrough and then applying it to Microsoft's products or to advance society. And so now a lot of our collaborations with the local universities will be of that flavor.
Yeah.
You know, joint investigations and really fundamental research. And our collaborations with SingHealth will be looking at taking in some cases, taking the things we've developed and using it to help them and help their patients. In other cases, partnering with them on the really important problems that they're facing.
I think a lot of people don't appreciate that with the innovations of deep learning that came out in 2010, a lot of the work before that was mainly done in Microsoft research. I think things like the Bayesian optimization, we think about hyperparameters, and a lot of things about those how to do with neural networks is because of a lot of the speech processing algorithms that was pioneered out of the lab itself.
Well, I'm very proud of the early work that MSR did in AI,
yes.
But I also, have to acknowledge decades of work in academia and the giants in the field that and of course Jeff Hinton, who persevered through multiple AI winters to get us to where we are.
Yeah, I think that's where we get to now. The pace of generative AI is moving so fast. I mean, practically every week something comes out. How do you see this affecting, say, academic researchers and maybe even like in the infrastructure providers, be it any of the tech companies like Microsoft?
It's such a great question because, with one of the things that's I think happening now is that the tools that we're building accelerate the tools that we're building, and so now you can build a solution or investigate some new optimization that will help AI, but you can use AI to build those tools faster.
That's right.
And so what we're seeing is an acceleration of the turning of the technological and innovation crank. And then the other thing that I think is really striking is how general these models are. I mean, they pull structure out of unstructured data. And so it doesn't matter what field you're in, if there's structures in there, the models, and you have the data, the models can go and find it, and then you can use it. And so it's not just impacting or affecting the field of AI research, it's affecting most fields. One example that I love, that's near and dear to my heart as a computer architect, is that if you look at the historical stack, and you know this as well as I do, you have the CPUs and they have an instruction set, and then there's a compiler and an assembler and a linker and a loader and then a programming language. And there's all these layers that we've built to be human interpretable. And then we use tools to translate from one layer down to the other. But all those are kind of ad hoc things that we've built by hand over many decades. And I think AI is going to be able to define just completely new interfaces and just bust through them. And just completely change that whole hierarchy that I got trained on and I spent 30 years trying to master.
Yeah, it's something like, like the first time I started using Cursor and then trying to use prompt engineering to code but it actually upends all the things I've done in the past. I mean, went through normal COBOL programming to object-oriented programming, and then after that we have containers, all that different works and practices, and then we have GitHub actions and everything programmed properly, and then now we got upended again.
So I have a great example of that. So this past weekend, my wife was on a trip with a few of my kids, and so one of my third son and I sat down and decided to build a software project together for a project we were doing, and it was pretty complex, and we spent about 4 hours building it. And he doesn't code, but he's 13, but we were just having good family bonding. But the crazy thing was, I was using GitHub Copilot, I was using Sonnet 4,
yes.
I was using the agent mode, and it was the first time I've ever built a complex software solution where I did not look at a single line of code. And
yes.
It hit me then. And of course, vibe coding is now getting big, but lines of code are the new assembly language instructions. After the 70s, no one looked at assembly unless you were a specialist. We had compilers for that.
Well,
and now lines of code are becoming like assembly. It's just a whole different world.
And then we're going to be coding in English. That's going to be another layer of complexity.
Natural language intent, that's right.
So then there's the other part of it, right? Within the foundation models, there is the open source models alongside with the commercial closed ones. Mm-hmm. How do you view the open versus closed debate now in the generative AI landscape? It's
a big debate in the community, but one of the nice things about being at Microsoft is we are very open source friendly. I mean, MSR
yes.
publishes tons of open source stuff. From a product perspective, we just want to be the platform that empowers all of our customers and users the most. And so we're going to deploy the best open source models. We'll deploy the best closed source models that we have access to. So from a product perspective, we just want our customers to be happy. Mm. And so, we partner with other companies on closed source models. We ingest open source models and make them available. I think the one thing, the one advantage in the closed source models is that it's easier to guarantee safety. Mm. Because these models are getting very powerful, and you can you can monitor or at least restrict how they're being used. But Microsoft in general, we bought GitHub, we really believe in open source. Mm. So we're just like everyone else. We're just trying to navigate that. But I don't think we have we're not one or the other. We're just, it has to work for our customers.
So I guess given this open versus closed, then what about, say, for example, when we think about multimodal models and now reasoning agents, for example, what are the trends that you're closely watching? I mean, this year everybody says the year of the agentic AI, and we're starting to see different variations of how agents can go into systems
right.
on there. So
I think reasoning, it's got a lot of momentum. It seems really important. I think it's actually more important than even the momentum would suggest. I think these reasoning models are going to be incredibly foundational. And the reason, no pun intended, is that they can take steps and look at what they've done and backtrack and go forward. Now, and maybe this is me with my researcher hat on, I think where that gets incredibly powerful is when you start to have formal structures that you can reason yes. over and make correctness guarantees. So obviously now the models are doing that with code. They catch themselves making a mistake and fix it. Yes. But there's so many other areas where we should be able to project those other areas into formal spaces and then reason over those formal spaces and provide a strong guarantee of correctness and then execute it. So I think that the combination of formal logic structures and formal verification and reasoning models will allow us to do many, many more domains safely in a way that we really can't today with sort of the one-shot probabilistic models.
Do you think that, they're always talking about scaling laws and the more data you put in, are we actually hitting the wall? Or actually, there's so many dimensions, like for example, test time compute, for example,
right,
and all the different new metrics that's being drawn out in multimodal that we really are not, we're barely scratching the surface rather than hitting a wall.
As you know, I used to work in quantization, and we thought very hard about scaling laws and what is the scaling law for quantization and how does it affect, the economic scaling laws. What I'm seeing in research now is that is that it's not just one scaling along or two. It's like there are 10 dimensions of scaling, and we're scratching the surface in all of them. I think I don't know that there are hard limits until you run out of some resource. Like if you run out of data, then you're not going to be able to scale. But these models seem so general that as long as you have more of that resource, you'll be able to keep scaling.
In fact, I think they're now hiring PhD students to help them to look at complex academic problems. So the reinforcement learning is actually becoming more and more intense.
That's right. We're now getting better and better able to steer these models in interesting directions. Which, by the way, I think I'm also excited about, because in the labs we're starting to ask the question: how should we steer these models in a way that's good for human health and society, as opposed to just making the model more capable? So I think that's going to be a really promising direction.
I want to ask this question. You led Project Catapult and Brainwave. What are the key design choices that drove their success?
I think one, maybe I'll answer at a high level and then a more specific level. I mean, for me as a researcher, it's always been about getting out into a new space and struggling and then waiting until you have clarity. And once you have clarity, then you just go and you're kind of relentless.
Totally agree with you. That's how I felt when I'm doing my PhD.
That's right. And it's hard to be out because very often when you're doing something that is going to be important and new, by definition, it shouldn't make sense to everyone else. So everyone kind of looks at you and scratches their head. And so when we said, why are you doing what you're doing? And so when we started on the Catapult journey, what I was really setting out to do, we were looking at CPU trends and saw that per core, per CPU performance was leveling off. And we convinced ourselves that specialized hardware for different applications was going to be the future. And so we started building customized hardware, trying to make a general platform for Microsoft's cloud that you could program different applications onto. And so so we decided to take a bet on FPGAs because you could program them, and it was a first step towards specialized, a whole fleet of specialized ASICs once the applications were big enough. But we kept getting the design wrong. Like we started off with a board that had 6 on it, and then if your application only needed 1, then 5 were stranded. If it needed 7, then you were screwed. So we networked them into a configurable fabric that hung off the back of a rack, 48 of them. And that was great. But then, the company wanted us to converge the infrastructure for Bing and Azure, and it was designed just for Bing. So then the third generation, we came up with this idea of putting the chip as a bump in the wire on the network path. And so then it could go out and talk to other chips.
Yes.
And so what we kind of built was a configurable plane of hardware acceleration. That's how Bing was using it. Azure ended up using that just to accelerate their networking stack, which they're still doing today.
Which also explains how your Azure computing platform is so ubiquitous among the large companies, because you have the kind of acceleration of the networks talking to each other at a very low latency situation.
I would love to think that's the reason, but the real reason is that the Azure team worked really hard and the sales teams worked really hard and everyone was just working really hard.
Okay. Yeah, but I want to get to quantum computing, right? Recently, you all introduced the Majorana 1 quantum chip actually using topological qubits.
Yep.
Something that I've been monitoring for a very long time because I'm a theoretical physicist by training. So there's a lot of long-standing challenge in stability.
So I should be interviewing you because you have the deep expertise.
I want to know a lot. No, I'm naturally curious, right? Because from your vantage point now leading global research, how is this shaping towards the future of quantum computing, and what are the milestones that we need to cross in order for us to reach maybe practical fault-tolerant type of quantum systems? Are we maybe a few years away, or maybe are we a decade or maybe 3 decades away?
Well, I certainly don't think we're 3 decades away, and the team has made great progress. One thing I want to really call out with that team, and they were in MSR, and then they graduated out into the business groups, and they've just been into the Azure team, and they've been pushing on that since then, is the courage they had to go after this crazy topological thing. I mean, they've been at it for 17 years.
Wow.
And people, and taking lots of slings and arrows, because after 10 years, people, your peers will just say, are you still doing that thing? Why haven't you given up yet? But the reason that they stuck with it so long, and now they're finally, showing that it works, and there's lots of work left to do, but I'm just so proud of them, is because the topological qubits are just inherently much more stable. because of the separation
That's right.
of the Cooper pairs.
Decoherence.
That's right.
Yes.
And so, like, if you're trying to do a more traditional qubit and do, lots of error correction as it decoheres, you need exponential numbers of error correction bits. It doesn't scale, or you're making them very big and they have to be very cold, and that doesn't scale. And so, really, what they've done is push down a path for, so many years towards what I think could ultimately be the quantum transistor.
Yes.
And I mean the field effect transistor, because there was point junction transistors and vacuum tubes before.
And we're
that.
going to have a quantum chip as well.
That's right. That's right. And so when the chip they have that they've built, in theory, it can hold millions of logical qubits.
Yeah.
Now they have to scale it. And so there's still a lot of work to be done. But in theory, that paradigm is so stable that if they get it to work at scale, it'll solve all these other problems that the other quantum approaches also have to solve, and they're going to have to solve it a different way.
I'm pretty impressed because it solves the decoherence problem that I usually ask a lot of people working in quantum computing.
Right.
How are you going to solve that, right?
Right.
But I think that 17-year journey is the much more interesting part of the story that I wanted to ask. How does Microsoft Research balance this kind of like blue sky foundational research against like more application-driven initiatives? Like how did this team actually have the morale to persist to get to this stage?
Well, there's three answers, and so with a caveat. So the first answer is that if you're going to be running a very elite research institution, you have to have the best people, and to have the best people, you have to trust the people and empower them. You can't hire a world expert in some area and then tell them what to do. They know more than you do. They're smarter than you are in their area, right? Yeah. So you've got to trust your people. And so one of our really foundational commitments, as I said before, to our people is we trust you. We're going to work to empower you. Go do the thing that you need to do. And so if somebody in the labs, wants to spend 5, 10, 15 years working on something they think is really important, they're empowered to do that. Now, of course, Peter, who runs, MSR globally, and I, and my peers, we review things, we give feedback, right? Because you don't want to, but if they think, no, you're wrong, I'm going to keep going. That's what they're supposed to be doing. So now on the quantum thing, of course, if you're spending a lot of money doing that personal vision of yours, the company's going to ask you, all right, what are we getting for the money? But one great thing about Microsoft that I really love about the company is how deeply intellectual it is. And this really comes from Bill and the founding. And Bill is still involved. We do reviews with him in MSR regularly. He gives great feedback. Satya is very curious. And so you go to those leaders and you ask them about our topological qubit program, and they understand, the strategy. They understand why we're doing what we're doing. The last hard questions, Bill will dive deep. But that team, just would show the progress and say, this is why we're doing what we're doing. We're going to address the decoherence problem. If we can get there, it's going to be really stable. Yes, it's a lot of money, but this would be a real boon for humanity. And so the company gave them the support to keep going.
Yeah, I think because of that, this year, I think Davos, a lot of people are talking about quantum computing. And I'm getting calls from venture capital firms that I advise about, can you give me a 1-hour rundown on quantum computing?
Oh,
I was
goodness.
like, this is getting great. But I think given that's the case, right, are we approaching, say, the limits of Moore's law? And what would be like a post-von Neumann type of computing world look like? I mean, we live in the logic gates, all these binary things that have all been invented in the 1920s, 1930s.
Right.
We're now in
all the Bell Labs.
Yeah, all the Bell Labs, and now we're in the next phase of that.
So maybe this higher level framing might be helpful. I think we're sitting on three fundamental modes or paradigms or pillars. I don't know what the right word is of computing. We have logic. You do an operation on a 0 or 1, like an AND gate.
Yes.
You have probability, and that's what the AI really is now.
Yeah.
I'm going to predict from some distribution am I going to get a 0 or a 1? And then you have quantum, where you have superimposed.
Yes, superimposed probabilities.
Superimposed, it's still probabilities, but they're superimposed, and they have that's right. It's a really important call. And so there's really these three modes, and they're very complementary and synergistic. And I think the really interesting thing is going to be some of the intersections between those fields, those three modes. Like if we get the big enough quantum computer working, or I should say when, you'll be able to generate all sorts of very accurate molecular data to train probabilistic models to produce new materials even better than they can today. And then you can synthesize those new materials in factories being driven by the logic stack.
Yeah,
right?
And I think they also have a lot of profound implications to cryptography.
That's right.
Specifically, quantum resistant codes. We are talking.
That's right.
Companies now talking about these quantum resistant codes that needs to be introduced into our password encryption. A lot of things are going to be another major change wave is coming.
Right. That's right. And so to come back to your question, we've talked about the quantum pillar. On the probabilistic pillar, which is AI, LLMs, all of that, I think it's just accelerating so fast. I mean, model costs are dropping 10x per year. We're just seeing, continued algorithmic silicon co-innovation. I think we've got decades of acceleration there. And then logic is, slowing down. And I think I think you were asking me about the popular version of Moore's Law, which is technological progress. There's of course, the formal version, which was Gordon Moore's 1964 paper, which talked about the rate at which transistors on a chip double.
But I think Moore's Law also would undergo a reformulation.
Yes. Well, yes. It has. But remember, I'm a computer architect, and I read his paper in grad school. And so when people ask me about Moore's Law, it's like dragging catnip in front of a cat. I have to answer the precise definition.
I totally understand that because you have to appreciate what comes before, and then you have to build on top of that. And then you have to take it to the next stage.
That's
on
right.
that. I want to switch course and talk about the concept of global research leadership from where you are. As the global head of Microsoft Research, how do you balance, say, long-term exploration with practical near-term impact?
Okay, well, I have to offer one connection by Peter Lee, who I work for, is the global head of MS. So I don't want to be claiming that that's me. But MSR has been around since the early 90s. We've had lots of crazy adventures. But one thing we figured out is that you have to be in exploration mode with people you trust, doing risky things that may not look like they make sense to discover new stuff. And it's always surprising and unpredictable. And then once you have that breakthrough, you then think about how to apply it, how to exploit it, how to use it. And we've actually gotten very good over the past 3 decades in taking those discoveries and getting them to scale. And we have lots of motions. We will take a research team and graduate them into the product groups. We will work with NGOs to solve some problem. We will have the product groups fund a center. We'll create an open consortium for some standard. We'll create V teams where people work together. So we'll create a mission lab to go chase after some important problem. So we've just learned all these different patterns and playbooks and over the years, and we're now pretty good saying, okay, we've had this breakthrough. What do we do with it?
Then, given that it's distributed, and also you also given autonomy to people to work on problems that matter them to most, and these are all very smart people. How do you get the innovation to synthesize across such a large and distributed network of labs? They have all different expertise, but then
that's right.
There must be something that maybe some high level principles within the lab to say, hey, maybe if we take this piece and this piece, we put it together, maybe this is something is of value.
That's right. So the framing that I think we like to use with our teams is we want everyone to do the most important work that they can, and sometimes that's powering into some new space or something you're really curious about and desperately want to understand. But sometimes it's taking something that you've invented or one of your colleagues has invented and taking it to solve a real problem or help people. And so we want to advance science, and that's the exploration. And we want to help, our customers, and we want to help society. And for any researcher at different times, the most important thing will be in those different buckets. Another thing that Peter and I and the rest of the MSR leadership do, we spend a lot of time going around to the labs, making connections, creating a culture where people can share things and work together and find those pieces. Sometimes, we see something and stitch them together. Sometimes, we just help create the environment, and then people do that naturally. And so a lot of the management and leadership's job is making connections and, helping people see some of the ways they might go and take stuff to scale. Because really, at the end of the day, if researchers care about deep science and deep understanding, and then also about having a lot of those things become real. And so I've always found that our people are highly incentivized to make stuff real and matter to people and help people, like, the cleft palate work, the Parkinson's work.
Yep.
If you can help millions of people with something that you're doing, you'll probably do that for a while rather than just going on to the next discovery.
So tell me, what's the one thing you know about building advanced AI infrastructure, or maybe leading global research orgs that very few people do?
Oh, what a great question. I think for leading research, it's the more curious you are and the more you know about different fields, like the more connections you can make. And Peter's very good at this. And so just that curiosity helps you to say this and this, where there's two people working in different domains, and say, oh, there's a connection here. This is something, by the way, that Bill Gates is, just phenomenal at, just because of the amount he's seen over the course of his career. I don't think it's something unique. I think it's something that research leaders learn, that just it's that oh, this and this make something
Reminds
surprising.
me of the Santa Fe Institute.
Yes.
Multidisciplinary research, or consilience is the word.
That's
to
right.
draw different fields together and put it together.
That's right.
There.
I like to say the tallest oaks grow from cracks in between the fields.
That's a better one. So what is the one question that you wish more people would ask you about AI research, but they don't?
Oh, I don't know how to answer that. I think for me, the one thing I really want to know, maybe is a slightly different take on it.
Yeah.
I just have this feeling in my gut that there is some mathematical theory underlying the compression of data that you need to make a prediction that's analogous to what Shannon did for digital codes and communication channels.
Right. Yeah. You're talking about the unstructured data, the ability for the foundation AI.
Yeah.
I think a lot of people haven't really done a lot of deeper architectural work into the transformer model.
Right.
What we are seeing is representations out of that model in the forms of BERT,
That's right.
GPT, and BART.
There's a deeper underlying.
Yes.
I think that there's a deeper underlying mathematical theory there.
Yes.
And again, this is just my gut as a researcher, and I'm probably totally wrong, that biology and evolution have figured out how to extract it and encode it in something that can run in 10 watts like our neocortex.
I agree with you on that.
And that when we finally understand this, we'll find out that all the hyperparameters in our brains have been set to be near that optimal theory.
Yeah, the way how our neurons are connected.
Yep.
Because it's the connectivity of the neurons that actually allow us to process thinking.
Yes, but they make connections, and then the connections get pruned, and the number of connections getting pruned every day is massive. So you're constantly sampling the information coming in and locking connections when there's something consistent that you need to make a successful prediction.
Interesting. I actually have that's a very good one, because I haven't thought about. I think we don't really understand the transformers architecture. I teach it as a course, but sometimes I'm also wondering some parts of it in my mind, that there are some non-linear properties that may be giving rise to these. What you're alluding to is a deeper mathematical language that embeds within them, but you're not sure how do you extract it out into a set of general rules, basically.
That's right. They're the transformers, and I mean, we understand why backprop works. We understand they're compressors, right? Like we understand the pieces, but I don't think we
understand how we put it all together.
That's right. There's a deeper theory of the underlying representation that they're learning that's not tied to 1,000-dimensional continuous spaces that the transformers are learning.
Interesting. Yeah, because the math is quite reminiscent of what I used to do in theoretical physics, like string theory. And there's a lot of embedded structures that's already hidden in theoretical physics with those models.
Except the transformers have more dimensions than string theory.
Yes.
That's a nerd joke.
Yes. It's linear. But it's linear. It's a great. I haven't had a chance to talk to someone so deep into the transformer architecture. But I have a traditional closing question. What does great look like for Microsoft research, especially in Asia, over the next 5 years?
So, great to me, from a management perspective, says that, great to me looks like we have amazing people who feel empowered and energized to do work that affects their societies and makes a real difference for people. I mean, of course, Microsoft's business, but the larger society. Like, I really want this AI revolution to be a big jump and a boon for humanity. And so great for me is that our labs are full of people that have a sense of purpose and passion and pride, and that are helping to do that. I have another secret fantasy, which is, I think, maybe more of an ego thing, but I would love, my secret dream, which is now not so secret, is 50 or 100 years from now, people look back at MSR today like the early days of Bell Labs,
Yes.
but for AI.
I actually thought that you have done one step beyond the Bell Labs by taking research global. Because in Bell Labs used to be only in one part of the region of the US, right?
Right, but this, I think we have to, because this is so important for all of humanity.
Yeah.
Like, we can't let one region decide, given the power of this AI stuff, what it means for everybody else. We have to do this together.
Many thanks, Doug, for coming on the show. And I think this is probably one of the most geeky conversations I have. So in closing up, 2 quick questions.
It was a lot of fun. Thank you.
Anything which have inspired you recently? You can share. Book, movie, anything else.
Anything that's inspired. I'm thinking of lots of research projects. So that's where my head is. Well, not too long ago, and this is maybe topical, I read The Idea Factory, which is about Bell Labs.
I read that book too.
Yeah,
Pretty good.
and I found that book incredibly inspiring. But that was a little bit while ago. Let me talk about one piece of work that I found inspiring. We have a team in MSR that's looking at using reinforcement learning to steer models having a multi-turn conversation so that the conversation can be more successful.
Yes.
And what happened in that review is we started talking about all the ways we could steer models to have conversations that helped people's mental health, or were engaging without tipping over into addiction,
Yes.
or could challenge them so they would do more critical thinking. And I came away from that meeting with my head spinning, saying, we have to steer these things for good in ways that are good for people. And so it's not a book or a movie, but that was something.
But that's interesting. I think that's where the responsible AI piece comes from.
That's
which
right.
is very important.
Yeah.
Instead of trying to get you into addiction, into challenging you to rethink your life and do something more positive.
That's right. Steering for good, maybe.
Yes.
Yeah.
So how would my audience be able to follow the work of Microsoft Research, latest developments?
Well, we have a website, research.microsoft.com. And you can go there, and of course, all our people are there. And we have, we do podcasts. Peter just did a podcast series. We have blogs. We put papers. I mean, it's a pretty active feed. We have well over 1,000 really smart people working really hard. So it's a lot. But just go to the website and you can find everything there.
I'll definitely point all the resources there in the transcript. And you can definitely find the podcast anywhere, everywhere. So subscribe to us. And of course, we'll be happy to take any feedback. So Doug, many thanks for sharing this quality time with me. And I look forward to speak to you again soon.
It was a real pleasure. Thank you.